Our next speaker is Marc-André Lemburg, who opened the conference yesterday. Today, Marc-André will talk about writing big apps. He will prove that despite being a scripting language, Python is a really good solution for designing large-scale, object-oriented apps. Designing large-scale applications in Python, Marc-André Lemburg.
Thank you. So this is a talk I already gave a few times. It was interesting because the first few times I gave it, people were not that interested in it. And as we progress and grow and people start writing large-scale applications in Python, people are actually getting interested in it. When I developed these things, this kind of design concept, there was pretty much, I think, nothing there in academia that I could refer to. I did not learn any of this at the university, so I basically learned most of this in the hard way by writing lots and lots of applications and failing, and then redoing things and trying to get better at it. And so these things are what I kind of distilled from this kind of process. So I'm not going to introduce myself again because I did that yesterday. This is the agenda. It's a rather long talk. It might get a bit boring at times. If you fall asleep, I don't mind. I can understand. So first I'm going to give a short introduction, then I'm going to go into this whole concept of application design, the things that I distilled from these processes that I went through, and then I'm going to give you a few hints at what to do before you actually start coding. So basically, this whole concept is a bit like this big design up front, but it doesn't have to be necessarily. I mean, you always have to have a good concept before you start writing something big, and you have to sit down and try to at least figure out the basic building blocks that you need. But the design is, the concept that I'm going to present is flexible enough to make it possible to later adapt the design to new requests and features. So let's start with the introduction. This is, I think, the basic theme behind Python. Python makes it very easy to write complex applications, fortunately. With the good side, there also comes a bad side. You can very easily create bad designs easily. So it's possible to... Python itself does not basically lead you to a proper design. You have to figure out that yourself. Fortunately, again, rewriting code is very easy. So if you make a mistake, you can easily change it and refactor it to make it work better. So when writing a big application in Python, it's very important to have a good application design and to think about this application design right up front. And I'm going to show you a bit about this kind of process. What's a large-scale application anyway in Python? I mean, if you go to C or if you go to Java, a large-scale application would probably be something that has 1 million lines of code. Now, if you compare C and Java to Python, you typically get this kind of ratio of 1 to 10. So 1 line in Python is about 10 lines of code in C. And so I figured that I would call large-scale applications something that has more than 100,000 lines of code of Python. For server-side applications and for client-side applications, it's even smaller. It starts about at 50,000 lines of code. So that's what I would call a large-scale application, where you actually have to sit down and do the design in order to come up with something that's really usable. Of course, in every Python application, you have lots and lots of third-party code. That third-party code does not count towards this lines of code measurement. So. And this is actually one thing that makes Python very, very popular. You have so many different extensions out there. There are so many things that have already been written for you. It's very important to go out there on PyPI, the Python package index, and try to find things that you can use, components that you can use in your application before you actually start writing them yourselves. So that's just something I wanted to say. That's very important. It makes Python very efficient in this process. So the next few slides are basically for, I don't know, this is if you talk to your CEO, you want to convince him to write something big in Python, then you can use these arguments. So what makes Python a good choice. It's highly efficient, so you can do really big things using small teams. You can do them quickly. You can easily adapt to your market. You don't have these big upfront investments. You don't have to set up a team with 50 team members to get something done like you do with C or Java, for example. It's very flexible in that you can easily react to changes in the requirements, and if you've ever done a real bigger project, then you know that changes always happen. It's very common to start with a project using one set of requirements and then at the end have a completely different set of requirements, because the customers change their minds about certain things. They want to, I've had customers that wanted to do a GUI application to implement their idea, and then halfway through the project they thought, well, GUI does not work that well, so let's do web. And then you have to adapt to these kinds of changes, which can be massive. But it's possible using Python. And you can very easily adapt to market changes as well. So if the customer sees that his particular model of what he or she had in mind when creating or getting the idea that they wanted implemented, you can easily adapt your project to that. So it's a good choice. Right, let's get to the interesting stuff. So what's a typical scenario that you have for writing bigger applications? You have complex interactions. So you need to interface with lots and lots of different things. With, say, I don't know, you have web services, you have humans sitting in front of a GUI, you have people using a browser accessing your system, you have different work concepts that you need to be implemented, and you have to adapt to all these things and make it possible for your application to work in this kinds of scenarios. So you have different ways of accessing all the data in your application and different ways of triggering stuff in your application. So how do you approach this? Well, the first thing that you have to realize is that there are different ways of different approaches of things that you have to implement in your application. You have a user interface. You have something that controls the information flow in your application. You need some kind of business logic, which basically just says that you need to make certain decisions based on the information that you have in your system and whatever your users want. And then, of course, you have to put this stuff somewhere, so you need a storage interface of some sort. So those are the basic things that you need. And if you look at this, this whole kind of design process, the whole application building process is very similar to what you do when you structure a company. I don't know, how many of you have companies? Not that many people, so mostly developers. So, I mean, if you look at say, a large company, then you always have departments, you have divisions in those companies. The departments and divisions, they usually map to different kinds of things that you need to do in a company, like sales, for example, development, marketing, controlling, and you need to define the responsibilities of all those different departments and divisions in your company. You need to create processes that make it possible for all these different departments to work together in some hopefully efficient way. And you need to put this into action to actually make everything work and make your company a success. And with applications, it's actually quite similar. So this is the design concept that I not came up with, because I mean this stuff is probably old. Maybe it's not. I don't know. I just look at yesterday we had this talk about the design talk yesterday, and I looked up this solid scheme that was presented in that talk, or one of the parts in that solid scheme, the single responsibility concept. That was actually published in, I think, 2003 it was. So it comes way after all of this, because I developed this in 1997 and did not have all these ways of just looking up stuff and just using concepts that were readily available. So there are two things in this design concept. One is that you use a structured approach. So you use the divide et impera, it's called in computer science. You try to solve a problem by dividing it into smaller pieces until you have manageable size pieces, and then you just solve those little pieces, put everything together again, and then you have solved your big problem. So this is one of the ways to do it. And because trying to make these divisions is not necessarily easy, you have to put some extra sauce with it and to make things easier. So this is what I call the Zen of Application Design. So you just, like with the Zen of Python, you use a few simple concepts that you try to adhere to make it possible to come up with proper decisions. So one is, of course, the KISS principle. I think you all know that. So you try to make things as simple as possible, but not simpler than that. The other one is you should not try to repeat yourself, the DRY principle. So it's usually better to think twice before doing something twice. And then very central to this concept is if something gets too complex, you try to decompose it into smaller parts, which is this divide et impera principle. And then if that doesn't help, if you get too many smaller pieces, then of course you have to look for other ways of doing things. And the way to do that is to apply some management, like what you do in a company. So if you follow these kinds of principles, and you always keep in mind that design is supposed to be something that's beautiful, then you probably come up with a good design. So let's start through this process, and this is where it gets boring because it's just iterative. So it just goes down the whole stack. I'm going to start with the application model and then go down to all the other models. So let's start with the application model. Right. So what's an application model? Well, it's basically the choice of where you want to have things happen in your application. So you have client-server model, which is very common. You can have a multi-threaded standalone application. You can have a single process, like a piping kind of application, where you just put in things on one side, process them, and then just output them on the other side. There are various other models. I'm not going to go into detail there. The most common one that web people usually have to deal with is the client-server one. So that's probably what you're going to use. Then the next thing is the processing model. So when you've defined your application model, you need to figure out how to, where to run your code and how to run your code. So you can run everything in a single process. That works well for example, piping solutions. You can have multiple processes if you want more stability. You can have multiple threads. For example, on Windows, you're pretty much stuck with threads because processes don't work well on Windows. Or you can use asynchronous processing, which brings you back to the single process kind of approach, but uses the async kind of method to process multiple requests. Or you can have a mix of everything. So once you've decided that, then the next thing is to look into the boundaries that you have in these in this processing model. So say you use multiple processes, then of course your data is split between the two processes, and you sometimes may need to get the data from one process to the other process. So you should decide on the processing model that makes most sense to you. For some applications, it may make a lot of sense to always use something that works in a single process, so you have all the data available in that single process. For other applications, like many web applications, it's a very usable approach is to go to the multiple process approach, because you usually only need the data for that one request to stay in your process. So this is what you can use as basis for deciding the processing model. Then you have your processing model set up. The next step is to choose the layer model that you want to use. So this always goes top to bottom. So at the top, you usually have the interaction with the outside world. In the middle, you have all the processing being done. And on the bottom level, you have data storage and interfacing to external services. So that's usually how you define your model. So you look at the data flow through your application. And typical examples of these layer models, well, one is the client application, just a standalone application. So you have a GUI, you have your application logic and the storage. Web applications, you all know. Batch processing is similar. You have a queue, you get your data, you process it, you put it somewhere else. Or again, you have a custom model that suits your needs better. So there are various ways of doing this. So let's have a look at the web application model, because that's probably what many of you know. So you have a standard situation. The client is your web browser. The web browser will do AJAX to get the data from the server side. The service needs to take a lot of load, and it has to do all the numeric stuff. It needs to be very stable. It needs to be fail-safe. If something breaks, you don't want the whole site to go down. You just want maybe one process to go down. It's connected to a database and needs to scale. Well, the usual stuff that you have for web applications, right? So this is what you'd, in this kind of design approach, that you choose for that kind of model. As application server model, you have the client-server model. Processing model would be the multiple process model, because you want to be fail-safe. If something breaks in your application, you don't want everything to break. And then the layer model is just a typical application server layer model that you have. So you have a database underneath, and then you have the different layers on top. So, okay, so now you've broken down things already pretty much. So now you have your layers. You can look at the different things that your layers have to implement. But writing those layers itself is usually complex, because there are usually lots of things going on. For example, if you have your business logic, then you usually have different things that need to be done. Same for the data management side. So you need to break down things again. You need to decompose things. And this is where it gets interesting. So what you do is you take the layer implementations and you break them up into components. And the components, they work really, really well in Python, because, like I mentioned yesterday, you have this concept of loose coupling your chunks of code, your components, because Python allows you very easily to just put everything together using the APIs. And so you don't have the strong binding like you have in Java or C, for example. You can create your components in a way that makes them easily replaceable. So you can by just defining the APIs of those components, you can easily replace the complete component with something new, which is something that's very useful to have in a project that evolves over time. And so what you do is you try to put the higher level concepts that you have in your application into those components, and you make them independent of each other. So the components should not depend on each other to do certain things. This is in the talk yesterday, every single component should just do that one thing that the component is supposed to do. It should just do what it's responsible for, not any other things. And you use multiple components for each of these building blocks. And so these are some examples of such components. So typical example is you have a database interface, you have something that does the user management for you, session management, caching. Maybe you have some services on the side that all your components will probably need, like logging, for example, is one such thing. Or you want to have a centralized error handling in your application. Those can be components as well. So you have things that map to your layers, but you also have things on the side that map to your to functionality that you always need in your application. Right, so what's the advantage? I already talked about the easily replaceable kind of idea. I once had a situation where I wrote an application. I went to the customer, tried to install it, and found that the application would not install because of some weird bug in the database interface. And because the database interface wasn't written by me, I couldn't easily just fix it. And what I did is I just replaced the complete database interface with a database interface to some other database. And that was done in a day. And I didn't have to change anything of the application because everything was loosely coupled. The whole application just used the API of that database component. And so this really made sense to do it that way. And if you need to, you can even change the processing model later on. So you can switch from, say, I don't know, you have a multi-threaded approach, you can switch to a multiple process approach if you need to. Because you only have these components, these small little islands, and they're connected to the other components, like, I don't know, maybe using ferries or something in that picture, to make everything work together without actually putting everything together like in this brick wall that I had yesterday. Right, I already talked about this, so I'm going to skip this. So how do you implement these things? First of all, well, what I usually always do is I try to implement the components in classes, and then I instantiate the class, and the object that comes out of that is my component object. I try to never keep state in those component objects, because keeping state in the objects themselves basically breaks your loose coupling, and you cannot easily shut down a component and fire up one again. This is very similar to what you have with containers nowadays. Back in those days we didn't have containers, so we had to put everything on one machine. But it's the same kind of principle. So you don't keep state in your components. You need to figure out how to keep state in some other way. I'm going to get to that later on. So this is a big picture model of how such an application could look like. So you have the interface layer up here. You have two components. This is, again, for a typical kind of web application server model. You have a request coming in, you have a response going out, so you have components for that. You have a server layer that takes care of the session management, user management. The application layer that does it processes the requests coming in using a handler. It does import, export for certain things, presentation for, I don't know, presenting certain data in maybe, say, a table or a graphics or something. Then you have validation, so you want to validate the incoming data or maybe even the outgoing data. And at the bottom you have the storage layer where you interface to databases or to file systems. And then on the side you can see these components there that take care of certain services that you need throughout the application. Now in this whole scheme there's one special component which is called, I call this system component in here. And this is a component that basically fires up your entire application and also shuts it down. And because, like I just said, I always used objects for these things, this is really just a single object. So it's implemented as class, but it's a single object, the system object. And this system object will then create all the other component objects that you see here, and all the components can talk to each other using that one system object. So this makes it possible to basically build your whole application and have it instantiated by one single object. And as you can imagine, you can use that principle to fire up several instances of your application in case you should need that. Maybe for testing, or maybe you want to scale up in some way. Right. I can basically skip this slide because I already talked about that. So, and this as well, that's nice. So the next thing I'm going to talk about is the management objects. So you now have your components, and in a few cases, like I said in the beginning, you break up things too much, you get too many little pieces, and you need to pretty much make those pieces work together again. So you have the management objects doing that. These are basically used to implement smaller tasks, smaller parts in your component objects. And they work directly with the data and the task objects. I'm going to come to in the next slide. They make it possible to break down your components even more. There's no good distinction between these management objects and the components themselves. Sometimes the components are the management objects. Sometimes you have one component object and you break that up into smaller management objects to make things more easily handleable. So at the very bottom you have the data objects. Like classes that implement certain, I don't know, say a data point or some data that you need in your application throughout your application. Say a report object that has certain parameters or well, these things. And next to the data objects, you have task objects. So, for example, you want to run a cron job somewhere, then you would put that into a task object, and you can use those objects to encapsulate either your data or the task that's supposed to be run. And you pass those to the management objects, and they do stuff with them and pass them around. So when you do this, this is how the information flow looks like in your application. So say you have a request coming in to handle some kind of export. The handler component will then go to the task manager. The task manager will find out, well, the user wants an export. It goes to the export task object. The export task object then knows, I need to do say, I don't know, an XML export because that's what the user chose for the export logic. The export object would then go up to the system component, and the system component knows the import-export component, and the export task object down here would just reference the import-export component, not the lower-level things down here. There's an API, or would be an API on the import-export component saying, I want an export, I want this export to be XML, I want it to go somewhere. Import-export component would then go to the export manager, and the export manager would know that it needs to talk to the XML export task object to actually do the export. And I talked about not keeping state in those component objects. The way to do that is to have a context data object that you associate with an incoming request or whatever the user is currently working on. And you have that nowadays in application servers as well. It's a very common thing to do, so you put everything into your, well, in Python it's usually a namespace object that you use for this, so you can put arbitrary stuff into that. And then you pass around this object to all the different objects that you have in your system. All the different APIs that you have in your system always take the context object as first parameter. And using that, you can then use your component objects without storing data in the components themselves or keeping state in there, but instead just passing around this context object and use that to hook everything together to make everything work. Right, that was pretty much the design step. Do you have any questions about this? Yeah? You don't have any microphones, yeah?
Did you have any contact with domain-driven design by Eric Evans? The
No.
concept? No? Okay.
No.
I would recommend looking at it. That's kind of similar. There is a lot more concepts described more in depth.
Yeah.
I can recommend to everyone.
Yeah, we should talk afterwards.
Yeah, it's already 10 years on the market, so
right.
worth looking at it because all of it is explained really nicely on 900 pages.
Perfect. Like I said, I did not have any kind of concept for this at the time. There was, I don't know whether there was research at the time, but I didn't learn any of this in your university. I don't know if it's done now. Well, I certainly hope it is, but in my days, we just learned about data structures and maybe how to do smart algorithms, but that was about it. I mean, so the basic building blocks of really low-level stuff and nothing. Right. So, I mean, using some of these concepts is really helps you if you want to use. I mean, you have a customer coming to you. You have this really complex application to build, and using some of these concepts really helps you to break things down, make them more handleable, manageable, and then to actually implement your stuff. And something that is very important in design, it should be a beautiful design. If it's not beautiful, something is wrong in your design, especially in Python, because if you do nice things in Python, then they will also look nice. It's very easy to write poorly designed things in Python. So this is also a criteria that you should use when designing software. if it looks nice and you feel good about it, then it's probably a good design. If you think that there are certain things in there that are not done right, it's probably true. It's not done right. So let's get back to the outside world, looking at structuring a company. So how would you map these ideas to structuring a company? So you have layer and component objects. Those are your departments and divisions. You have responsibilities that need to be defined. So you have your management objects and data and task objects, so the folders that you pass around in the company, or the emails that you send around, or documents. And you have processes defined in your company. And the processes are basically defined in that design using the APIs that you provide. So you tell your divisions or departments to use certain APIs, certain interactions with them to get certain things done. So if you use this structured approach, it can really go a long way. You can write really big applications with this. I originally used this approach for writing a complete web application server. That was around the time Zope was written, but it was a completely different design, and it was probably just as complex as Zope, but then I tried to sell it. Of course, I was way ahead of everybody. Nobody understood what I actually implemented, and so I couldn't sell it. So basically, just had to find some other way of then making money in the company. What then happened is I was hired by a company in London, and they wanted to implement a trading system in Python. They already had an application. They wanted that to go on the web. And then I helped them with that and used this approach again. It worked really well. It made this loose coupling made things work really well for them. They could easily exchange certain things. They had to adapt to new requirements in the market all the time. So that was really good. So this thing works. Okay, so we have a few minutes left. So I'm going to just scan through this a bit. These are more like, I don't know, hands-on things, tips that you can use. First of all, it's very important to structure everything in modules and packages. So the way that you do this is you just look at your design, you take your components, you take your management objects and the classes that you've defined, put them and break those modules at the component or the management object boundaries. And so you get small modules. You try to prevent import loops, which are really nasty in your applications. You always use absolute import paths. This is especially important for large-scale applications because you can easily get lost if you have hundreds of modules in your application. You immediately want to know where to look in your application if you want to find something. This is very important. And so if you go up from the component layer, from the component objects into the layer module and the application module, you should completely switch to, well, what I usually do is I switch to different parts, different paths on the file system, because that makes it very easy to decouple things even more. So not even Python has access to the different directories. And you can, for example, you can have something like a web server running here. You have a server running here that reads quotes from some data servers, and then maybe you have a different machine that just takes care of distributing data to, say, customers, say, sending out emails or reports. So you can separate out things like that. Then, of course, you have the data objects and the task objects. You should try not to use the primitives that you have in Python for these things, because sooner or later, you're always going to find that you need to add on something. For example, if you put everything into tuples and then you remember that, well, the different positions in that tuple mean different things, sooner or later you're going to want to add something to the end, or you want to replace the order in that tuple, and that's going to cause a lot of work if you want to do refactoring for that. So it's usually better to have a data object that basically just has attributes. You can easily add an attribute to an object, or remove it, or rename it. It's much easier than doing this in tuples or dictionaries or lists. So use namespace objects. They really make a difference. Then you should use methods, of course, for simple tasks. You should try not to make the methods too simple because it just causes a lot of overhead and slows down your application. Python is not very good at function calls. So if you can avoid doing a function call, you should probably think about doing that if you have something that's time critical. If not, then you can just break them down to really small parts. So if you're doing something that's not performance critical, it's usually better to have a better design, have a better style, and use more methods. And then if you have APIs that you define on your components, for example, then you should group them into bundles of methods. This can be done in multiple ways. You can have just chunks that you separate using different, I don't know, like with a comment, for example, or you can even go to a nice feature in Python, the mixing classes, and then just define your APIs, the chunks that you have in your APIs in mixing classes, and then use those mixing classes on various different classes, the component classes that you have, and import things into those so that you don't have to re-implement them out all the time. So this is a very nice thing to do. Then if something gets too complex, if something starts to look ugly, or you have to go through hoops to get something implemented because your design does not really address that particular need that you currently have, you should always go through a phase of refactoring your code. So refactoring in this case means that you try to restructure everything in a way that makes it possible to more easily implement what you just want to do. It also means splitting out functions, for example, into smaller parts, so to better structure them. I would just refer to the talk yesterday on how to do these things. Trying to figure out exactly to what scale you need to do these things is a bit, it needs a bit experience. So because if you split it up too much, then your code base is going to blow up. You're going to get too much code. If you don't do it enough, then you're going to have to do this refactoring over and over again. What's very important in refactoring is that, and this kind of ties into this rabbit hole idea, sometimes when you try to refactor something, you get stuck. And you find that you cannot refactor some code because the code is simply not made for that. And then you just stop and throw it away and rewrite it. And this is very important. You have to be daring when it comes to refactoring your code. Right, and this is a topic that is not being addressed enough, I think. Everyone talks about testing all the way, all kinds of different interfaces, but people usually forget to write proper documentation for that code. And you always have to remind yourself that other developers are going to read your code, and they don't necessarily want to go through all the different lines of code that you've written to figure out what it's actually doing. They also don't want to always have to look through the tests that you've written to figure out what a certain method is supposed to do and what you expect of that method. So you should really write the contract, the external contract of your method or your function into the docstring to make it very easy for other developers to get on board, to understand what you need to do. And then, of course, you need to structure your code. So add some bit of white space, add a few comments here and there in your code. I don't necessarily consider that doing that a bad design. It may be a hint of needing some refactoring sometimes, but it's generally a good idea to make it nice and readable. And Python is usually nice and readable. Right, I've already talked about this. Of course, you need to write tests. Don't want to say that this is not needed. You should try to use some of these. Well, extreme programming is probably an old technique by now. What I always do before checking in something, I always try to read the code and not actually run it. So I just actually try to go through the flow of control of what I've just written and try to understand what the code does, or try to understand whether it actually does what I want it to do. before checking in things. And then, of course, I write tests for actually making sure that things do work as I intended them. But this, the reading of the code itself already provides a good increase in efficiency, because you always spot the typos that you've done, or maybe you have certain branches in your code that never get executed for some reason. Maybe you've just made a mistake, or maybe you've restructured it in a way that's not really suitable. And then I can only refer to Brandon's talk today. You should try to make use of your tools as much as possible. So one thing that I always try to do is I always use the editor's autocompletion tool to write code, to write variable names, for example, or function names or method names. Because, of course, the editor that only knows about stuff that's already there, so it will automatically give you the right spelling of a function or a variable name. And so you avoid typos using that. And that was it. Any questions?